Okay, the YouTube should be live. Do we need to let people in the meeting or do they join automatically?
They join automatically, so that people are already joining now. And do you have the presentation for sharing?
Yeah, I have that open here. All right. Peter, Archit, are you ready?
Yes.
Okay. And then after I'm done, I will. How do I make Peter the presenter?
I think I am now co-host before you arrived, so I can just grab the screen.
Okay, excellent. Good.
So can you share, Oliver?
Yep.
Okay, got it. Okay, we're seeing that. So I'll go ahead and hit the start recording button now. Does that sound okay? I think I can do that. Okay, looks like the recording started. And I guess for attendees, we'll probably wait another minute or so before we get going.
Okay.
Good. So Eric, this is Mike. Looks like you guys got everything running. Streaming seems to be working.
Yeah, Shoemaker, it's a metaphor. Well, don't call it out. Trying to be like artful with language.
So just ask that those of you who are attendees,
Well,
go ahead and mute your microphone.
yeah, I muted that person. I know her. But yes, if you're unmuted, please make sure you're muted during the presentation. Then I would say we get started, Eric.
Yes, let's go for it.
Okay. Well, me turn on my video for a moment. So welcome to the IBIPSA USA Education Committee webinar. Today, we will hear from Peter Garforth and Archit Naik about municipal scale energy and carbon reduction strategy modeling. Very interesting and relevant topic in the current situation for the energy security, energy safety of the country. Peter and Archit have very interesting material to present. I'll do a quick housekeeping here. So the course is registered with AIA for continuing professional education credits. If you need credits, I think, well, you can request your certificates through IBIPSA, or for other organizations, I think you can self-report. If you have any questions, please let us know. In order to support IBIPSA USA, everyone who is not a member yet, who is on the call, and everyone you know in your networks and your families and your organizations, please consider joining IBIPSA USA. The more members we have, the stronger our community is and the more impact we can have and the more we can achieve. Here, if you have questions about membership, here's the link, IBIPSA USA, or you can email to membership@ibipsa.us if you have any questions. Quick introduction for the speakers. So Peter Galforth is not an energy modeler. So it's not too often that we have education webinars in IBIPSA with non-energy modelers. Peter Galforth is heading Galforth International based in Toledo, Ohio, and in Brussels and Belgium. So transatlantic footprint, extraordinary career experience as a C-level executive in multiple global organizations. And over the last 12, 15 years, I had the pleasure to work with Peter on energy master planning for communities, for campuses, for cities, for counties. And we will hear more about that from Peter today. Co-presenting is Archit Naik. Archit is one of my colleagues here at Baumann Consulting. He's an energy modeling expert, one of the best I've known, and he's been working on integrated energy master plannings with Peter for the last few years. And so together from Peter and Archit, we will hear about municipal scale energy and carbon reduction strategy modeling. Quickly, all participants on the call, please make sure you mute yourself, especially if you have the YouTube call running in parallel behind. It will create a feedback. I will mute people, but if you mute yourself, that would help. From here, I hand it over to Peter and Archit. Take it away.
Thank you, Oliver. I just want to check everybody can see my screen.
We can.
Excellent. Well, thank you very much. I feel quite humbled presenting to a group of expert building modelers, and I'm a simple failed electrical engineer who went into business development. So we're going to dive in. We're going to cover a lot of ground in the next approximately 45 minutes. And I intentionally put this slide up, this picture up front. And for the purpose of this discussion, I'd like us to think of the municipality as the energy object, and the buildings, the homes, the cars, and the factories as system components of the energy and economic system. This happens to be a community we have just completed a plan on. It's Oakville in Ontario, community of about 200,000 people. So that's sort of our starting point. So think our building is a community, not the individual buildings, they're the components. Let me just make sure the introductions, I won't spend any more time on myself and Ajit, and thank you very much, Oliver, for the kind introduction. I want to add one person who will not be speaking today, which is our colleague, Gerd Fleischhammer, who's a community integration energy specialist, and he's based in Germany. I'm not sure if Gerd's online watching. If he is, good evening. And Gerd was a major contributor to the background of this presentation. I'd also like to make some brief acknowledgements. Firstly, to the team that Oliver and myself have worked with, and these are some very talented individuals around the world in Denmark, in the UK, in Canada, and the USA, each bringing their own particular expertise of the community space, including political leadership. We have somebody who's been a 3-term mayor of a significant community, structured financing, and so on. So we see energy and climate planning for a community as way beyond a technical discussion. And I'd also like to recognize our community partners, and I put that very specifically as partners, not customers, because all of our teams are always very collaborative. And at the end of every project, we are smarter than we were at the beginning, and our processes and tools are updated accordingly to head into the next project. So we're going to quickly go through the rationale for community energy transformation, look at the kind of goals we see in North America, the strategic framework that is typically used in the simulation tools. Then Ajit will spend a few minutes discussing generalized modeling. And then we will go to somebody is not muted, I'm getting feedback. And then into a very quick simulation of what we have loosely termed any city North America, which is a typical North American city. So what's the rationale? Why are communities looking at energy transformation? Obviously, a major driver is various forms of climate action pressures coming not only from the scientific facts on the ground, but also the voters, investors, and employers within their municipalities. There is increasingly expectations coming from government, scientific, social communities to put pressure on emissions reductions. And then we are seeing, irrespective of national policy, and that's obviously a conversation that could go on for much time, we are seeing communities specifically committing, and I've just summarized a few of them here, but in North America alone, there's somewhere between 500 and 700 cities that essentially have emissions targets aligned with the Paris Climate Agreement. Cities in general use about 70% of all the primary energy, and primary energy in turn causes about 70% of the carbon emissions contributing to climate change. So clearly the impact of energy in cities on this topic is major. The second driver is the fact that we have many, many more technical tools at much lower cost and much easier integration. So we're seeing a convergence of digital and energy technology. We're getting more and more cost-effective technologies that allow us to bring energy systems closer and closer to the end use. The economic and environmental burden of the existing system inefficiencies is increasingly coming into focus and can now be addressed with changing technology. And last but not least, energy security is becoming a growing factor, especially with changing climate. At least one of our customers is now actively managing fair weather flooding. So we are now looking at the energy security aspects as the technology allows us to bring our energy systems closer to the end use. In effect, we can begin to customize our energy systems at a community level or a municipal level rather than the more traditional regional, provincial, and national levels. Our third driver, which is becoming increasingly in focus, is the current global pandemic. And I just went online and tagged in green recovery, and you saw some pictures that came up immediately. And we are seeing national and pan-national policy coming together increasingly that says we are actually in an opportunity, which is a crisis and an opportunity at the same time. to create large amounts of employment quickly with sustained economic development, and we are in a good situation to do that in serving the climate recovery. So we are looking at a bottom line where communities have clear economic pressures to create employment and immediate economic development, and also the long-term pressure to remain competitive for the sustained future. So with those three drivers, we come to, why are those 500 North American communities in some way embracing energy transitions? And I've listed some of them here, but basically the bottom line is to make those communities competitive, attractive, destinations for investment, destinations to live in, and serve their voters for the long haul. If we look at the plans of those 500, 600, 700 North American cities, we see common themes in terms of the goals that we're looking at. They are very aggressive. They are often treated more as political grandstanding rather than as hard tactical goals. So what we are going to do today is explore these goals, but in the context of a real city. And every community has its own way of phrasing these goals, but they generally fall into 4 buckets. They fall into the environmental bucket, which is saying, and generally speaking, that has a very strong greenhouse gas reduction element, where typically we're looking at a 2-decade 50 to 60 to 70% reduction, with a target to be close to net zero emissions by 2050, which is very much in line with the scientific evidence and the multinational agreements like the Paris Agreement. Then we look at the efficiency targets. Generally speaking, we see at least a 50% source energy efficiency within 20 years. Sometimes more aggressive, sometimes less, but generally in the 40 to 60% range. And then the economic targets, where depending how the community is interpreting cost and economic opportunity, it's usually in 3 buckets. Cost reductions generally in the range of $5 billion over 20 years, cumulatively over 20 years for 100,000 population. 500 jobs in the first decade, and that aligns with this immediate economic development pressure and recovery. And then recognizing that most communities have economic development targets, and those target industries like biomedicine, light energy, electronics, et cetera, and each of those industry sectors, target employment sectors, has their own energy needs. And if the community can configure to meet those energy needs, then that in turn becomes a supporting element of economic development. And last but not least, increasingly importantly, is improving reliability at the local level with levers and options that the community can deploy. So those are typically the buckets. So we'll sort of take those as a general guiding framework. Some communities tend to focus on one rather than the other. A few of them have a clear, balanced, holistic view of environment, economy, and efficiency. Okay, so once you've got those goals, they sort of sit at the top of a strategic framework. And this one, I want to thank the town of Oakville. This is adapted from a recent community energy planning exercise from their work. And you see those 3 buckets of goals: energy, emissions, and economic. Then guiding principles that lay across all sectors, public and private, around environment, economic, and reliability. And these are usually some fairly specific guiding principles. Then the main energy consuming factors, sectors: homes, buildings, efficiency, transportation, homes, buildings, industry, transportation, and then reconfiguring local supply and distribution. Then the information and optimization overlay, sometimes bracketed generically as smart city. And then the necessary shifts of at the community level of policy, governance, and market practices. One of the things we see all too often is an excessive focus on getting perfection in the planning and forgetting that at the end of the day, the ultimate thing that matters is what are we going to do in the next 5 years to deliver those 20, 30-year targets. So you'll see at the bottom here, this whole process leads to a very clear first 5-year priority scale projects and resources. So let's talk about simulation at the municipal level. Like a building, like a neighborhood, the simulation is simply an exercise to bring data and assumptions together to explore optional choices to meet targets. So the targets are established by the community goals, and we've just summarized those. Now we need a comprehensive simulation that says, if we do this, 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 and this together, what is going to get us closest to those economic, environmental, and technical targets? Once we have that simulation, then we get into the hard work of developing the strategic recommendations and the delivery. So looking at the elements we need to simulate, this is sort of a 30,000-foot view of it at a municipal level. And again, I arbitrarily chose the map of Oakville as the example in the center there, where we are looking at the components that all fit together of making our existing buildings more efficient, homes, etc. I won't read through all the boxes. We have more interesting things to talk about, but you'll notice we've got local energy supply elements, local fuel elements. In addition, of course, we have the traditional grids and networks. You'll also notice the map of the community is broken into what we term energy planning districts. So we can do mapping and simulation overlays at the level of the districts. In this, a community of 200,000 people, there's 26 districts, which align with the municipal official planning. The key thing in this picture is this is not a buffet where you pick the piece you like and ignore the piece you don't. Once I'm at the municipal level, my energy object is the total. I have one solution and many elements. So at the end of the day, we got to come up with one game plan spread over 20, 30 years, and then mobilize the community to deliver all the moving parts. It begins with demand mapping, and Ajit will spend a little more time on the stationary energy, but that's the homes, buildings, and industry demand, typically a half to 2/3 of the energy use of a community. And at the minute we're talking simulation, we got to get pretty granular. We carve it out by traditional sectors. Sometimes we'll create a sector. For example, in the county of Essex, we're working when a community has one of the largest concentrations of commercial greenhouses actually in the world, but certainly in North America. Huge energy consumer, so we created a sector specifically for that municipality. Then the categories, the end users, the utilities that serve the end users, and then what we're calling the case, the simulation case, the base case or business as usual, and the efficient case where we tweak different scenarios over time, year by year, to see how that pool of category ties together. This is always built from municipal property roles. So typically in a community of 100,000 people, we'd be talking about 40 to 50,000 locations for each of these pieces of the puzzle. Then obviously transportation, which is typically a half to a third of the energy footprint of a community. Then sorry, there's a little bit of noise in the background there. There we would have an equally granular breakdown of the trips, the length, who's in the trips, how many are passengers, the modes, the vehicle types, the fuel, including electricity or none. If I'm walking to complete my trip or cycling, I need no fuel other than a cup of coffee in the morning. And then again, the case of this granular assessment by neighborhood and by all those various categories. And then each of those becomes a simulation variable. Then that energy demand needs to be integrated into a tool which allows us to combine and test various combinations of measures and intensity of measures and timing of measures against their cost, environmental, and energy impacts. This is the typical integration tool, recognizing that in every community there is always some adaptation. So we're working with components and modules which have evolved over time. As I say, every project we end up getting another realization of how we can improve things, and there's always a little tweak. But broadly speaking, I'll walk down this quickly. Is my mouse visible? I'm assuming it is. The first layer is the geographic layers of the community, which is the neighborhoods, the energy planning districts, always chosen to align with the normal planning districts of the city. Then the sectors, and those are the end user categories. Then the solution elements, which is business as usual or base case. And then the various configurations of efficiency, energy supply, utility network, district energies, renewable supplies, and so on within the community by district and neighborhood and property or end use category. And then out of this comes the results in terms of efficiency and so on. Then we have the possibility, even in a normal model, to simulate various changes of obvious things like, do we include a lot of renewables or not? Do we include a lot of high efficiency new construction or not? What happens if the price outlooks are different from what we assume? And so on and so on. So these are, if you like, our simulation buttons that allows us to see the impacts on the entire community interactively between the energy balance, the greenhouse gas balance, and the financial balance. And then our graphics, and just about every time we do a community plan, we end up with new graphic flexibility, because there is always a realization that to communicate to one group of stakeholders, be it the financial community, the construction community, there is a better way of communicating and presenting what are essentially very complicated multidimensional thoughts. But in terms of standard graphics, obviously, we have things like the baseline pies, the bar graphs, the simulation pictures, the GIS mapping by energy planning district. So for example, if we want to look at the electricity use in the single family homes by neighborhood on single family homes that are 30 years old, then we can basically carve out those pieces of the data set and create GIS maps of the pictures. And then Sankey diagrams, and we'll show you a few of those. It's an energy system. So like energy system, be it a steam engine or an entire municipality, we can make Sankey diagrams and energy flow pictures. And those are also part of the puzzle. They are great communication tools. So that's the very quick look at the tool set. I'll now hand over to Ajit, who will take us quickly through the generalized modeling of the built environment. Today, we're not going to look at the generalized modeling of the transportation environment, but I'll be happy to answer any offline questions on that if there's interest. So with that, I will pause and hand over to Ajit.
All right, thank you, Peter. I appreciate that. Hopefully you guys can hear me okay. Yeah, thank you. So basically, I want to talk a little bit about our generalized modeling approach for the built environment. Peter, could you advance the screen? when looking at a municipality or a community with 200,000 people and thousands of buildings, it's a really tall order to model the entire building stock. So we typically take a generalized approach. That is, based on municipal property records, we sort the entire building stock into building types and age brackets. We can have as many as 20, 25 building types, as many as 5 age brackets. We can end up with hundreds of different models in representing an entire community. These energy models are then used to assess a baseline, which is calibrated to the utility data at the neighborhood level. Then it's also used to test energy efficiency measures. This is sort of like a single archetype approach to it. There are new technologies to model building stock statistically being developed by NREL, including Comstock and ResStock. But regardless of the approach to take generalized modeling, it can be used and integrated into our set of tools. Could you advance the slide, Peter? Sorry, could you advance the slide, Peter? Thanks. So really, our generalized models are not specific. They're supposed to represent sort of the average building, but they're always tailored locally. So our starting point for North American projects, at least, are everybody's favorite Pnnl and DOE reference models, which most of you on the call are probably familiar with. We use a variety of energy modeling software, but when working with these models, they're primarily in Energy Plus, and we use BuildSim Hub's Python environment to batch modify the models, calibrate them, and run them quickly in the cloud. When you're running 150 models every iteration, this time can build up quite quickly. We benchmark archetype performance against global best practices, including publications from Europe like PEPBD and KFW. And we always tailor our archetypes to whatever is relevant locally. So for example, archetypes in Canada would be tailored to the local Ontario building code for projects in Ontario, and using publications and research done by Natural Resources Canada, Canada's counterpart to the DOE. Sometimes we have to create new archetypes. As Peter mentioned, we worked on a project in the county of Essex, Ontario, the largest collection of greenhouses in North America. And for this, we had to create a greenhouse archetype. We had to learn a whole lot about greenhouses. We connected with the Ontario Greenhouse Vegetable Growers Association. We've done a survey and a study with local utility companies to sort of profile the greenhouse building stock as well as their energy use patterns. So by connecting with local groups like this, we were able to develop building energy models for these greenhouses and calibrate them to these longitudinal studies that had been performed. Could you advance the slide, Peter? These models are always localized. For example, we modified here's an example from a project in Windsor, Ontario. So these, the inputs for these models would be normalized to current historical building codes. So these would be the Ontario building code as they changed through the years in 74, 97, and 2011. When we developed these models in Ontario originally for some cities in the suburbs of Toronto, when we moved on to a project in the city of Windsor, which has a much older housing stock, the city sustainability staff had actually performed a ton of blower-door testing. When our models came showing way too little heating energy, we connected with them and sort of reviewed their blower-door studies that they had done on a few hundred homes, and we realized that the infiltration rates in Windsor were significantly higher. So by going through an iterative process, always working with our teaming partners, we were able to come up with a reasonable set of inputs that defined the building stock as it was, and we got a very good match to meter. Could you advance the slide, Peter? Then we develop typically efficiency cases. We test our base case parametrically. We test lots of different options, but always with the mind of feasibility. For example, when talking about retrofitting houses, it's much easier to add insulation to an existing single-family home's roof than it is to its walls. So while we would assume that a roof could be re-insulated, we wouldn't necessarily assume a wall could be re-insulated due to the difficulties and feasibility in making that happen. We also look for synergies with existing programs. For example, again, for this model in Windsor, Ontario, that city is in a flood zone and has incentives to install sump pumps, which provide a good opportunity to insulate the junction at the wall foundation. So we looked for opportunities to represent an efficiency case that was not only effective, but also reasonable for the climate and locality. Could you advance the slide, Peter? And once our models are kind of developed, we look at them each on a pretty rigorous basis. This was a project that we worked on in Germany, a multifamily home, relatively recent construction. We always take a look at our base case versus our efficiency cases in terms of annual energy use breakdown, but we also look at peak demand and our demand profiles. So once we make sure that our buildings and our archetypes make sense at an individual building basis, we then take it and match it to the meter at the energy planning district. If it's a bad match, we come back to the drawing board to again recalibrate our models, usually again in terms of infiltration and plug loads, to use as a calibration lever until our results make sense, not only at a building level, but also at an energy planning district level. And once we've matched the meter, then it's back to Peter to integrate this into the wider municipal study. Thanks, Peter. Go ahead.
My sound on. So what we're going to do now in the remaining 17 minutes is quickly take a look at a place called Any City North America. And it has very specific characteristics. In other words, we have simulated a real city, and we're going to look at some aspects of simulating that city as a total. So where is, or what is Energy City North America? It's a city in the upper Midwest or Southern Ontario. It's got a couple of 100,000 people. It's going to grow about 25% over the next 30 years. Employment's going to grow in line with population. It's got about 80,000 planning lots in its property profile. A lot of them residential. It's got about 1.5 billion passenger miles traveled every year for people going about their business in one form or another, including commercial traffic and transit traffic. But instead of being, it's in an electricity grid, which is pretty average for the USA, about 500 kilograms per megawatt hour of greenhouse gas equivalent, which we are, as we can see around as coal plants are closed and more natural gas and more wind comes on stream, we're expecting to track down to about 200 kilograms in the next 30 years. And then our natural gas network is again typical for North America, about 200 kilograms per megawatt hour greenhouse gas. And that's going to drop to about 150 rounded kilograms as the natural gas networks follow the trend that we're seeing around the world of strategically including biogas and renewable hydrogen into the networks. So we're expecting a degree of decarbonization of the natural gas, and that's clearly outside of the control of the municipality or the city. The city itself is one of those 500 cities with a climate vision or an energy transformation vision, which in the US and Canada represents well over 100 million population. So it's a big chunk of the pie. Where they're shooting for a 60% greenhouse gas reduction within 20 years, and then heading towards something you could say is approximating to near net zero by 2050. They're looking to save at least 10 billion in the next 2 decades and looking for a 40% source efficiency gain. This is deep transformation. But these goals are very typical. We see them in municipal plans all over the US and Canada. So with this as our starting point, and I just want to briefly take a look at the pictures on the left. We go all the way from and these have all followed this simulation model, all the way from a city of over 2 million people in China, Urumqi, then a city of 35,000 people in Michigan, Holland, Michigan. Both of those have got significant contributions to their greenhouse gas reduction, energy reliability, and local economic activity as a result of taking a holistic view of their energy challenges. And then there's other communities, and sometimes the municipality is not a municipality. There's a picture on the left there of the Portsmouth Naval Shipyard, the US Naval Shipyard in Kittery, Maine, which is in effect a municipality that happens to be a military base. But so in other words, this technique applies to any complex multi-dimensional environment. We said it's the We're simulating an energy system. This will look very familiar to you if you just put you called that gray box a building. That's basically what we're looking at. It just happens to be a much bigger energy object. So we have source energy, which is crude oil, electricity, and gas, feeding the energy system, the urban area. The site energy is delivered either at the fuel pump or the meters. Then we have all the end uses that we've already talked about in buildings, factories, and homes and vehicles. Some of that energy is useful, some of it is waste, but we pay for the waste anyway because we have to support the entire system. And then where does the money we spend on energy go? How much of it leaves the urban area and how much of it is reinvested within the urban area, and how much greenhouse gas emissions does the urban area create? And if you look at those four blue boxes are essentially the driving framing targets of the community energy plan or the energy transformation plan or the energy and climate plan or whatever name it's given. So this is sort of the big picture of how we look at it. So any city, this 200,000 city, it is built off actual municipal records. We use the municipal records, property records from a real city to make the simulation. We just tweak the energy supply systems a little bit to make it northern Midwest, upper Midwest average. And you see here immediately, if I'm looking at source energy efficiency and I don't look at transportation and I don't look at homes and I only focus on the office buildings and the city hall and the odd factory, I'm clearly not going to hit my macro targets. So this is now reducing that very complex set of data and assumptions to the beginning of aha, here's how I got to begin to prioritize my thinking. This is the source energy by sector. Then we go to the greenhouse gas emissions by sector. And you see here the built environment or the stationary energy, factories, homes, and buildings, is a little less, and the transportation is a little more. So if I'm pulling my levers on greenhouse gas emissions, I really can't ignore my transportation. And I certainly, it wouldn't make sense to get obsessive about the institutional property and forget everything else. So again, it's back to this prioritization. This particular city, which as I say, is built on real data, so it would be this would not be unlike a small Toledo, where I'm sitting at the moment. 10.5 metric tons greenhouse gas per capita, which is roughly 4 times urban best practice in a similar climate, which today would probably be, your benchmark would be Copenhagen, which would sit at about 2.5 metric tons per capita. So one of the reasons we always do global benchmarking, Ajit mentioned it, is it gives us some data reference points beyond the immediate experience of the local team or the community, or even some of the local associations and industries. So we always bring in a global best practice benchmark. Sometimes there is a local best practice, which happens to be global, sometimes not. But either way, it gives us a reference beyond the local experience. Then we run out a base case or business as usual, year by year, sector by sector, utility by utility, neighborhood by neighborhood. So there's obviously hundreds of bar charts we could show you or maps. This is just the by sector. And this is business as usual. It gets a little more efficient over time. It's the combination of slightly more efficient construction, code anticipation, and slightly more efficient vehicles. And you see the community goal there for 2040. We're a long way off that goal under business as usual. Then we look at our emissions and we saw our grids were getting lower carbon. So that means we got a wind in our back from the utilities. They're helping us at least address one piece of the puzzle. So even though this particular city is growing 25%, its emissions actually fall by in the range of 15 to 20%. But there you see those two goals hanging there, the community goal in 2040 and this 2050 kind of international goal of a 90% to net zero by 2050. And it's a very, very big gap from even though our grids and our networks, gas networks, have got significantly lower carbon than they are today. So in other words, we cannot rely on, let's say, somebody else to deliver our targets. So then we go to the cost, and this is, we always look at a lower range of cost risk and a higher range of cost risk for the utilities. And we see this one brings us in at, I'm just going to move that off, I'm sorry. This one brings us in at roughly tripling over the 30 years coming. So this says we've either got to live with a cost escalation, or we have to treat the cost escalation as an opportunity. Put my mouse in the right screen, there we go. And if we then go to the higher range of risk, that tripling suddenly, or more than, yeah, nearly tripling, suddenly goes into a quadrupling or more. And now we are looking at a very major economic cost risk, or we could be looking at a very major economic opportunity. So it's how we deal with future cost outlooks will define not only the urgency of our actions, but the attractiveness of our actions. Nobody has a perfect crystal ball, so this is why we always include a lower and higher range of cost, and we always spend quite a bit of time simulating what ifs around the cost, because they obviously ultimately drive the investments, which ultimately will transform the energy systems. So this is, you saw that big picture graphic of the elements that go into the simulations. This is more granular. Again, we don't have time to go through them in detail. I want to highlight a couple. One of them is in that top row, where we say we are going to retrofit 80% of our existing homes and 60% of our existing buildings within over 20 years. So it's not next Wednesday, it's year by year. And we will use, and you saw the models that Ajit had up there with the efficiency and so on, and we have that for, you know, every archetype. And then we will model those, we will use the modeled outputs as the drivers of the simulation. An 80% renovation rate for homes is enormously high. The best we have found of any residential retrofit program in North America is in the 3 to 4 to 5% range so far on many programs which have been running for at least 10 to 15 years. In other words, this is unquestionably transformational breakthrough. Then I'll highlight another one, which is the idea of the eco districts or the net zero neighborhoods, which I'm sure many of you are involved with building modeling. Here we've assumed that at least 30% of new construction will fall into the category of those neighborhood high efficiency developments, where the efficiency of the buildings may exceed the minimum requirements of local code. And then there's a lot of detailed things, and I just want to flag another one, which is a big mover, is the electrification of the transportation fleet. And we're assuming by 2040, 20 years from now, 80% of the light vehicles, so cars, SUVs, and light pickup trucks are electric, and 80% of the buses and light rail are also electric. So, and again, very, very high penetration, because that's the entire fleet. So that includes, you know, vehicles which are running today that somebody may keep, you know, running for at least the next 20, 30 years. So in other words, this is an incredibly aggressive transformation of the energy profile of any city. Any city is the city we're looking at. It's a real city in terms of the simulation. So source energy efficiency, we said, remember the community had a 40% target, which by the way, would still exceed the average we would see in a global best practice today. We could find plenty of cities in Northern Germany and Scandinavia, which already were 50, 60% more efficient on average in total than a North American average. So in other words, our benchmarking to some extent drives the efficiency target. So we see here this simulation, this incredibly aggressive transformation of the community has hit that 40% target in 20 years. but that assumes everything plays together and everything gets moving and year by year is implemented. On greenhouse gas emissions, it exceeds the 60% goal the community set itself for 2040, but it's still in the range of somewhere between 70 and 100% away from the internationally recognized goal of near net zero by 2050. But it is an enormous, enormous transformation. So anytime we see a community saying we're going to be net zero by 2035, our first question is how? Where's your year-by-year game plan to get there by sector, public and private? And of course, we generally find that there usually is no plan. There's often very worthwhile visions, but no plans, and certainly no simulation to inform the plans. Then in the cost, what does any city capture? They capture about $18 billion over 30 years. And that, to a first approximation, if we multiply that by something between 5 and 7, I'll leave the economists to explain that. That gives us a sense of the investment potential that could be applied to implementing the solution that creates the transformation. It's obviously a circular conversation. We don't get the benefit without the investment, but I need to understand the potential to invest to generate all those measures that create the savings. So doing a technical evaluation simulation without doing an economic simulation is frankly interesting but worthless, because it doesn't ultimately take us on a pathway to implementation. On the higher range, that 18 billion becomes 30 billion, and this is a very useful communication, because if those things are not done or are done very half-heartedly and light touch, then the actual risk to the community is $30 billion they're going to have to spend, most of which will leave the community to simply stay in business and be the working community. So this is a picture not only of opportunity, it's also a picture of risk. Then we can, of course, look at the energy balance. And this is the Sankey diagram of 2050 business as usual. This is 2050 simulated. So any city, simulation 1, headline target communication. It met the community goal of 60% reduction. That little yellow arrow on the right is the 90% 2050 goal. So it's still got a way to go to close the gap, but it's made enormous progress from the baseline, which of course is the 0. And it generates $10 billion by 2040. So we can tick that box and say, broadly speaking, we've hit the big picture economic and environmental targets. And now, what if? This is the power of a simulation. It allows us now to say, what if? Well, what if? So I've actually taken the same picture, and I've now just added simulation 1, so we can keep a visual on the reference point. So this is exactly the same as the previous result. This is the result of simulation 1 with no what ifs. So what if all new construction simply meets code? In other words, no net zero neighborhoods. Sorry. Excuse me. Then, excuse me, I've got to kill a, there we go. Okay, apologies for that. I had a timer. So what if we had no new construction? And I'll just go back to the previous slide. You see that needle drops a little bit. Whoops. Sorry, I'm going back too far. There we go. So here's the complete simulation. Oh, my apologies for that. Here's a complete simulation. And here is no eco districts, no net zero neighborhoods, no passive houses, no et cetera, et cetera. So that's the impact. We saved a little less money on the cumulative energy cost. It's about, goes from 10.2 to 10.1. And we made a very small contribution to greenhouse gas reduction. Now let's go to the next one. What if the efficiency strategies fail? In other words, instead of 80% of the homes, we only retrofit 30%. And instead of 60% of the buildings, 20%. And industry now meets the median good performance of 0.5% per year as opposed to 1.5%. Our cumulative energy savings now falls below the 10 billion target, and our emissions clearly are falling below the 60% target and making the challenge to hit the 2050 target much more difficult. I'm not accumulating these, so in other words, we reset everything. This is just the efficiency strategies. If we now go to, we have no district energy services, no new solar PV within the boundary, so behind the meter solar PV. So we remove our thermal integration in the higher density neighborhoods, and our greenhouse gas now slips below our 60% target, and our savings basically is now about a billion below our target. If we now go to, what if our travel habits change? Only half of the bus and light vehicle fleet is electric. Instead of 1 in 10 trips by foot, bike or bus, we now are 1 in 20. And our average trips, instead of being 50% shorter, are 7.5% shorter. Massive impact on the emissions, somewhat and a significant impact on the costs. So if all of our measures fall short, that's where we are. We are 4 billion below our economic cost savings target. We are substantially below our simulation, and we have got an almost impossible gap to a near net zero by 2050. And remember, these are the 2040 figures we're looking at here. So if that's and I would just want to make one last comment. If all the measures fall short in this simulation, any city would still be doing far, far more than any community we found in North America yet. In other words, falling short is not drifting to an average mean. It itself is transformational. So this really gives us a sense of scale. So closing thoughts, I'm running a minute or two over, I apologize. Basically, municipal scale simulation, you've seen the three bricks to simulate the entire community. This then is the first step in data continuity to what we call second level plans, where we can do neighborhood plans, retrofit plans, utility plans, all of which are the contributing elements to the simulation, to the municipal big picture. So bottom line, simulation allows us to have conversations driven by data, not opinions, which is equally true at a building level, but it's doubly true at a community level. And last but not least, it's a prerequisite pathway to get to large-scale implementation quickly, and it's a fabulous way to communicate with non-technical stakeholders who really have to be engaged if we're going to have any chance of delivering these kind of programs. So with that, I will stop. I apologize for running a few minutes over and take any questions. Personally, I'm flexible on time, so I'm not sure how tight we have to be to the 1 hour.
All right. Thank you very much, Peter and Ajit. Great presentation with a lot of material. We do have a few questions. I would just take them from the top as they came in. The first one actually came in, I think, while Ajit was presenting. And that question is, what techniques and data do you use to match the meter? Are you using building energy data?
Thanks. Yes, we are. We're using utility data. Depending on project to project, that can come in at varying levels of granularity on a per building basis up to a per neighborhood or a per block basis. But typically, we apply like M&V principles, tuning the model inputs until we get a decent acceptability of fit. This doesn't take into account the uncertainty in that, but we are. As we continue to develop our models, we're beginning to take an approach that includes uncertainty as well.
Depending on the community, we often get the utility data either by postcode or zip code or by actual planning neighborhood. So it depends on the community and the utilities, but we generally get it by neighborhood in some form.
Okay, thank you. Next question is, I'm curious how you are handling all the various assumptions over the next 30 years, PEV uptake, increasing CAFE standards, changeover in building stock and growth, electrification of existing building stocks, decarbonization of the grid.
That's the power of a simulation, because obviously if you get 10 people in the room and ask them what electricity is going to cost 10 years from now, you're going to get 10 different answers. So the beauty of the simulation is if there is a significant non-alignment over assumptions, it is possible to put in different assumptions, see the impact on the total community, and in some cases, an assumption may be the impact of an assumption may be relatively minor at the community level and can be sort of managed over time. If it is significant, then it may require another dialogue before one agrees on the principles. If there's major uncertainty on an assumption, then clearly the plan itself and the recommendations maybe has to have an exit ramp or a plan A and a plan B, depending on which way the future comes out. But you can't even have those conversations without a simulation.
Okay. Next question. When you talk about any city, does it mean that you have created a virtual model of a prototype city? If so, how did you decide how a prototype city looks like in terms of number, age, type of buildings? Have you created an energy model per building for the city model to produce the results?
Simple answer is we didn't create the pool of property. We took it from an existing program. So it's actually taken from a real community of about 200,000 people. We simply changed the utility variables to be more typical of, and the same for transportation data. So it's from a real community, but we simply changed the utility variables to be more typical of an upper Midwest US average. So, and that's basically what we did. So it's as close to a real city as it could be, with an obvious adjustment to be upper Midwest average.
Okay. And have you created an energy model per building for the city model to produce the results?
Yes, exactly the way, exactly the way Ajit described.
Okay.
Yeah, that would be again using a generalized approach. That would be, for single-family homes, it would be different generations of 5 different buildings describing different generations of a single-family home, so on and so forth throughout all sectors of buildings within this fictional community.
Okay. Next questions, and there are still coming questions in here. My coworkers used to retrofit HVAC in residences, but stopped doing so because it wasn't profitable. In order to get to 80% retrofitted, this practice would need to become more commonplace and more profitable. Do you see this shift as possible?
Yes, we have developed business cases for at least three municipalities, one of 100,000, one of 250, and one of 200,000. It's an investment grade business case. And like most, and the question is a very good question, by the way, because at the moment in the vast majority of North America, doing a comprehensive retrofit of an existing home is typically economically unattractive relative to the cost of energy and the value of the saved energy. So clearly there is a requirement to make the delivery of retrofits much more cost effective than it is today, which means it has to be more standardized, more comprehensive, and much better supply logistics. So, and without that, you're never going to achieve the scale. So the answer is you've got to transform not only the customer perception of a retrofit, you've also got to transform the supply channel for the retrofits. So it's a very real challenge, and the question is very, very relevant, because if we don't get the 80%, you see what happened on the meter.
Okay, next question. Have you ever used these models to simulate the demand flexibility in buildings?
Ajit, do you want to take that?
Sure, and that's a great question. Right now, we're using we integrate the results on an annual basis, not on an hourly basis. But this is something that we're literally we're talking about right now. So we haven't done this yet, but this is on the radar for our next project.
I would make one comment that when we take these principles and apply them at a campus level, campus could be a neighborhood, it could be a military base, then the level of the building modeling would be more close to individual modeling, even though it would still use generalized techniques. So yeah, it kind of looks the same, but it's a little different once you get down to that second level, what we call the second level plan, the neighborhood plan or the campus plan.
Yeah, and I guess that's a good point. We have done it, but typically on a campus level, not on a full municipal basis. So that is in the works.
Okay, next question. New York City will begin taxing building emissions in excess of a limit, but there is currently no data to determine the feasibility of the goal. It means all stakeholders meeting, the city's goal is predicated to electrification, but the success of electrification is predicated on improvement of grid infrastructure and blend of source energy. Ideally, we would be able to compare the rate of these improvements and moderate how rapidly stakeholders switch to electric, but no such data is available. Are there computational limits to modeling at the municipal level that would preclude making such a comparison?
No, in fact, we didn't have time in the available time, but if it in the when you read through the slides, you'll see in that detailed description of simulation 1, we did include electric heat pumps in the simulation for both retrofit and new construction under certain conditions, and we also include thermal integration, district energy as part of the puzzle. Clearly, in the simulation, we could move to all electric, and we could take out the thermal integration. In other words, the simulation would allow the tool structure would allow you to take that at neighborhood or municipal level and actually evaluate the impacts of full electrification. This is increasingly a challenge that we're getting, not just in New York City, we see it everywhere. There's this sort of idea that somehow if we can just electrify everything, in 10 years, we're going to fix all the problems. The reality is it doesn't work that way when you actually start integrating it in the simulation. So that's why, so the answer is yes, we can simulate all electric transportation options, all electric heating options, and see what it does to the grid demand and to the impacts within the community itself.
Okay, I have 2 more questions here in the chat. I would say we just continue. I know we're over time, but I think it's good to keep going. So next question is, did you have any problems with privacy issues regarding utility data for residential and privately owned commercial buildings?
Yes, sometimes by law, sometimes by habit. But generally speaking, we would neither ask for nor get individual user data. And in some cases by law, if there are, for example, if we ask by postcode and there are less than X number of customers, typically somewhere 3 or 5 customers within that postcode, which could happen with large commercial and industrial environments, then we will not get the data, and that data will be pulled into a other category. So where we have large individual users, we in a community, we will generally approach them as a community member, usually through another community stakeholder, and ask for their permission to share their data. And in most cases, they're happy to do that. In terms of residential data, we never get individual building level data, user level data. So we are always working on neighborhood or postcode.
Okay, there's actually one question here that came in through the YouTube channel where we're live streaming here. What software do you use for simulating the transportation sector?
The Untitled set at the moment is essentially an advanced application of Excel. There's lots of macros, and there's shared file structures. I would leave the detailed description to my colleague in Germany, Gerd, who's the tool master. The transportation sector, that is one of the most difficult ones, not so much to do the technical integration. That's relatively straightforward. It's actually getting the raw data. There is very limited comprehensive average data for transportation, frankly, anywhere in the world. And we are beginning to see that challenge being addressed. Google is now trying to do transportation simulation using some of their data from Google Maps and Google Maps searches. However, it's the area where arguably the problem is not the tool, the problem is the raw data. So we have to be fairly creative when we're assembling it. But we simulate it still with a high level of granularity, because even if we are using somewhat broad assumptions, as those assumptions can be narrowed as data gets better, we can always go back into our data set and update it. So in other words, the granularity is important in the tool, even if the assumptions are broad at the beginning.
Okay. Other question, what methods do you use for the calibration of the energy model?
I'll leave that over to Ajit once we've done the match to meter. Ajit, do you want to take that?
Yeah, sure. Typically, we apply just like an M&V type approach for it. So where we play with inputs. Typically for heating, we look at infiltration is a major one of our control variables. For electricity use, we focus on unregulated loads such as plug loads. And using, again, it's kind of a balance here. We can only match, as Peter said, on like a block basis when it comes to residential buildings. So our calibration process is also similarly sort of high level as well.
Okay. I have one last question that came also in through the YouTube channel. How important is energy flexibility in the management and planning process of communities?
Incredibly important. And one of the major aspects, and we didn't have time to go through it today, was that reliability bar at the bottom. The fourth goal. The creating a local integrated system, so very much as we kind of simulated here, actually creates many flexibility pathways. So for example, if we have a significant portion of integrated thermal, district heating and cooling, maybe we simulate it running on natural gas and electricity, but down the road, we know we can put waste heat into that system. We can put biogas boilers. We could even put renewable electric boilers. In other words, we have created flexibility by municipal integration. And the obvious thing, if I've got a significant amount of local power generation, I can keep the lights on in a hurricane and so on. So there are many aspects which are reliability and future flexibility aspects of local integration, which we didn't really have time to go through today, but they are critically important.
Okay. Just one other question that came in. What are the simulation environments software recommended most suitable that take into account the many aspects mentioned?
One of the reasons we've developed what we developed, and that I was writing an email today about something completely different, but this started actually in this whole journey of this team anyway, started in doing some simulation modeling for a energy plan in a city in Poland in 1990s, early 1990s, was that there were no municipal level simulation tools available. And where they were available, they were tending to come from trying to integrate complex tools at the building level or at the vehicle level, and then integrate them upwards. So they kind of look, they drowned on their own weight. So we believe we have come up with an approach which goes the other way, where we take the community as the energy object, we simulate it down to the level of granularity that the data permits, and then that creates the pathway to link to the more traditional detailed simulation models for a small campus, for a neighborhood or an individual building. So we basically feel there's actually a gap in this conversation at the city and big neighborhood level.
Okay, there's still questions coming in, but we're quarter hour past the time. I would say we will collect those questions and we will answer them offline. We will post them to the BIPSA website. The seminar is being recorded and will be posted and can be watched again through the BIPSA USA webinar, USA website, and is accessible. If you have additional questions, let them come and we will respond to them offline. At that point, big thank you to Peter and Archit. That was a fantastic presentation. Even though I hear Peter talk a lot, every time I learn something new and take more things away. So I look forward to the next time, Peter, you're presenting. So thanks to both speakers. IBIPSA USA, if you like that program, consider joining IBIPSA USA, become a member, become active in the committees. This is a seminar that is hosted by the Education Committee. And if you want to be part of that, the meeting times are posted on social media and also on the website. Everyone is welcome to join and to contribute. Other than that, I'll leave it here and say thanks to everyone. We had a fantastic turnout, and I'm very positively surprised how many people actually stayed on the call here in the meeting, even beyond the time. That tells me that it was relevant, that it was interesting. Peter, Archit, thank you again, and everyone have a great day.